All right, so now we're going to take a look at some of the examples in ALEKS for the lipids section. And this first one here is just understanding some of the basic descriptions you have of fatty acids and some of the components of the different lipids. So we have here to draw a skeletal aligned structure for a saturated fatty acid with 10 carbons. All right, so let's just remind ourselves, saturated, I'll abbreviate that as SATD. This means that we have only carbon-carbon single bonds. Okay, and then fatty acid Fa means that it's just simply a long chain, long carbon chain, carboxylic acid, right? Remember the carboxylic acid functional group, C double bond O, OH. So if I want to draw a 10 carbon fatty acid, I can draw 10 carbons in a row. So that's my first, second, that's a third, fourth, fifth, sixth, seventh, 8, 9, and 10. Right, so you'll notice the shortcut for drawing your carbon chain that makes it look really uniform and neat. So let's double check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need a carbon double bonded to an O. So there's one bond. There's another, and then I have my OH that's going to be right here. So I can change these. There's my OH. And then I have my oxygen here at the top. Now double check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Saturated all carbon-carbon single bonds, and then my carboxylic acid functional group. All right, and that's how you do that. If it's asking for unsaturated, then you'd need at least one carbon-carbon double bond somewhere in here. If it says polyunsaturated, then you'll need to have multiple carbon-carbon double bonds. All right, and then the next one we're going to take a look at has to do with some of the physical properties of the fatty acids, specifically the melting points of fatty acids. And this then would depend on the length of the carbon chain, and then also the number of carbon-to-carbon double bonds. Okay, so if everything is the same, if there are no other differences, but just the length of the carbon chain, if the number of carbons increases, the melting point increases as well, right? That's just a direct relationship between size of the molecule and the melting point. Now, that's if you have the same type of fatty acid. In other words, if you're comparing saturated fatty acids, if you're comparing monounsaturated to each other, if you're comparing polyunsaturated to each other, you just look at the number of carbons. If the number of carbons is the same, but the number of double bonds, the number of carbon-carbon double bonds increases, then what we see is that the melting point actually decreases, right? So the double bonds, what they do is they prevent the molecules from packing close together. They're more spread out. They're going to be more like a liquid rather than a solid. So that's what we're going to look for when it comes to determining or comparing melting points of a fatty acid. Let's take a look at the first one. So this one here has a total of 20 CH2s, CH3, and a C double bond O. So this has actually 20, 21, 22 carbons. Okay, and then because we don't see any double bonds in here, this would be saturated, right? Carbon-carbon single bonds when you see it in the condensed structure. The second one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 carbons, and this is also saturated. If you look at the third one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. And then this is going to be unsaturated because we have this carbon-carbon double bond in here. And then the fourth one has 18 CH2s, 19, 20 carbons. And this is saturated as well. All right. So right away, we can see that there are 3 of these that are saturated. And the only difference between them is the number of carbons. Okay, so we said that if you're comparing those 3 that are saturated, as the number of carbons increases, the melting point is going to increase as well. So out of these 3, right, this the one with the 18 carbon is going to have the lowest melting point. The one with 22 is going to have the highest melting point. And then the 20 is going to be sort of in the middle. Now, there's one of these that is unsaturated, and it's actually smaller than the others, and that's the 16 carbon. So the fact that it's smaller right away, we can quickly say that it's going to have the lowest melting point. And because it has at least one carbon-carbon double bond, that's going to make it more like a liquid. It's not going to pack close together to others of the same type of molecule. So this then is going to have, that just confirms that that's going to have the lowest melting point. All right, we have the highest, and then the only 2 left would be the 18 and the 20, while the one with the higher number of carbons, because both of these are saturated, comparing these 2, this would have the second highest melting point, and then this one here would have the third highest, etc. So if we were to rank these by increasing melting point, we start with the lowest. That will be the unsaturated. So that's the lowest. The next one will be the one with the 18 carbons. That's this one. Obviously, the highest is going to be the first one, and then that leaves number 3. The second highest one will be the one at the bottom. All right, so you want to, when you compare these, look to see the number of carbons that are present, and also look to see whether they're saturated versus unsaturated. All right, so in this one, we're taking a look to see, check our understanding of the organization of the cell membrane and the types of molecules that could be embedded in the cell membrane. Okay, so remember the organization of the cell membrane. It's a phospholipid bilayer. So we have 2 layers, sort of like this. So you have 1 layer of phospholipids on the top. And, well, let me draw it slightly differently so that we can actually orient ourselves to the question. So you have 1 layer, let's say on the left side, another layer here on the right side. All right, so this is how the cell membrane is going to look, sort of in a block diagram. Okay, so this is the bilayer. We have 1 layer here and another layer next to it. Okay, so in blue, there's 1 layer, and in green, there's the other layer. So it's important to note how this bilayer is organized. On the outside of the bilayer, we have the polar regions. Okay, so this would be polar here, and this polar on the outside of the inner layer. The middle portion of the bilayer is non-polar. That's where the tails hang out with each other, because they're all non-polar. Remember, like dissolves like. So what this question is asking is to decide whether each of the molecules can be found embedded in the outer surface of the cell membrane. So the outer surface is polar. Right? So what we need to decide is, as you look at our molecules, do the molecules have polar region or polar end and a non-polar end? Okay, so they need to have a polar end that can embed in the polar region and a non-polar end that can be away from the non-polar region, from the polar region. So when we look at the first one, this first one here, you'll see that this is made up only of carbons and H's all the way through. This entire molecule is non-polar, so it cannot embed in the outer surface of the cell membrane, right? The outer surface of the cell membrane is polar, and we need we need one end of the molecule to be polar. If we look at the second one, right? We'll see that, yes, there are lots of C's and H's, mostly non-polar, but this region here with the charge is polar. So we have a polar end, we have a non-polar end. Yes, that can embed. Where is this going to embed? Well, as it's drawn, that's going to stick right here on this side of it, of the membrane. So the cell membrane then is going to be to the left of this molecule, right? So the membrane then is going to be on this side. That molecule with its polar end can embed right here. The second one, we have something similar. Oh, I'm sorry, the third one, we have something similar happening. There's our polar region on the left side, and the non-polar region on the right side, mostly C's and H's. Yes, we have polar and non-polar. And then because the polar region is on the left, the membrane is going to be to that side. For the last one, again, mostly C's and H's, but we do have the nitrogen here with a positive charge. That's polar. The rest of it is non-polar. Yes, because the polar region is on the right, it can then embed on this side of the membrane. So the membrane is going to be on the right side. So as you go through these options, that's what you want to look for, right? Do the molecules have a polar end and a non-polar end that would allow them to be embedded in the outer membrane? And then just look to see which side of the molecule is the polar region located. That's the side that the membrane is going to be on. Okay, so in this question, we're going to take a look at classifying our lipids that contain fatty acids in them. So you want to take a sort of a global overall look at your lipids and the different categories that they belong to. So this is not really looking at really, really minute details, but it's looking to see whether you can recognize the different categories. So if we take a look at this first one here, right, you want to look at the functional groups. Those are what are going to tell you the families that these are going to belong to. So you'll notice there's a carboxylic acid side of it here, and it's made up of a long carbon chain. So this is a long carbon chain carboxylic acid. That by definition is a fatty acid, right? So A, this option is a fatty acid. If you look at B, we can see that we have a 3-carbon backbone right here in the middle. We have 2 ester bonds to fatty acids on the right side, so one here, and then another one with their long carbon tails. And then we have this phosphate group right here on the 3rd carbon. And right away, once you see phosphate in it, you're thinking some sort of a phospho something. But in order for that to be a phospholipid, we need it shouldn't have this portion here connected to it. So this actually does not belong to any of the categories that are listed that are shown on the options. If you look at C, so C here has the ester in the middle, and then we have a long carbon chain on one side and a long carbon chain on the other. That is a really telltale sign that we're looking at a wax, right? A wax is just an ester of a long chain alcohol on the right side and a fatty acid, long carbon chain carboxylic acid here on the left. If you look at D, there's our glycerol backbone. We have 3 ester bonds to fatty acids, so that would be a triacylglycerol. It's also a triglyceride, right? So we'll have 2 terms that are used for that one. All right, so let's see down here. So I did mention the one with the phosphate group in it, right? So that is that actually is a phospholipid. My apologies. This one here. So once you see the phosphate group in there, right, that tells you that it belongs to the phospholipid category. All right, so the next one we're going to take a look at has to do with matching some of the structures and the functions of some common lipids. So you'll be provided with a description of a molecule or a compound, and you have to select from the options A, B, C, or D whether any of these actually match up to the description that's there, right? So you'll need to probably have your textbook with you as you go through this, just to confirm what some of the structures actually look like. So if we take a look, start at the bottom here. Number 4 says this class of pain relievers that include aspirin and ibuprofen work by interfering with the synthesis of this type of molecule, right? So these usually work by interfering, especially for pain relievers and inflammation, anti-inflammatory drugs, these interfere with the production of prostaglandins. All right, so let's see if we see the structure for prostaglandin. This looks like a steroid nucleus, so that's not a prostaglandin. This one here, B, looks like there's a triester, triacylglycerol, or triglyceride. This looks like it could be a prostaglandin. However, if you look closely at it, right, we have the chain snaking around with the ring structure here, but this portion doesn't have the carboxylic acid functional group, right? Whereas D actually does. So D would be your prostaglandin. So that would be what a description of what number 4 does. If we look at number 3, cell membranes in both plants and animals are primarily made of this kind of molecule. So cell membranes are made up of a phospholipid bilayer, right? So we need to find a phospholipid. D obviously isn't, that's a prostaglandin. C is not. B is a regular triglyceride, and A is not either. So none of them actually fit that description. Number 2, this kind of molecule is not soluble in water, so it must be transported in the blood in complexes called lipoproteins. All right, so lipoproteins are combinations of proteins and lipids, specifically triglycerides or triacylglycerols. So we're looking for a triglyceride. A isn't. B definitely looks like it is, right? There's your 3 ester functional groups connecting the glycerol backbone to our fatty acids. And let's just confirm C isn't a triglyceride, and neither is D. Number 1, this kind of molecule defines the nature and function of cells by directing which proteins are synthesized. That's a classic definition of nucleic acids, and that actually isn't in any of these. Nucleic acids actually come in a couple of chapters down the road. All right, and in this question, we're taking a look at the breakdown or the hydrolysis of triacylglycerols, either under acidic or basic conditions. So regular acidic hydrolysis, or under basic conditions, that would be saponification. So in this case, we're asked to provide the products. In some cases, you'll be asked to work backwards and provide the reactants. So here we have a triglyceride or a triacylglycerol. And we're subjecting it to sodium hydroxide, right? So remember, sodium hydroxide is your clue that it's undergoing saponification. Okay, so saponification is just the basic hydrolysis. Of an ester. Okay, so we're going to break the ester bonds. And what we're going to end up with are going to be the original alcohol and the salt of the fatty acid. All right, and in this case, with our so for hydrolysis of the triacylglycerol or the triglyceride, the alcohol ends up being glycerol, and the salt of the fatty acid, that's our soap that we end up making there. Okay, so that's what we need to draw for our product. So let's take a look here at our example. So we have a CH2O, C double bond O, and that's connected to a CH2 5 times, CH double bond CH, CH2, CH3, and we have our second carbon, CH connected to the O, C double bond O. We have the same, looks like the same fatty acid here on the right. And then on the third carbon in our glycerol, we have our ester bond again, and that looks to be connected to the same fatty acid also. All right, so if I'm taking this now and I'm going to react it with NaOH, and I have 3 NaOHs to show that there are 3 positions that this is going to happen, we're going to break the ester bonds right here. Okay, so I have this entire fragment then on the left side that I make. So I have my CH2OH, that's connected to my CHOH, that's connected to my CH2OH, right? So that's my glycerol that I get. That's this fragment there in right. And then on the left, I'm sorry, on the right side, I'm going to have each of these, right? So in green, we'll try to draw these. And all I'm doing is I'm drawing the fragments that result first, right? That's the quickest way to do these. That's to ensure that you don't make any of the simple mistakes that can crop up. So all I'm going to do now is to complete this soap or the salt of the fatty acid, right? The H here from the NaOH completed the hydroxyl groups for the glycerol. The Na and the O now come in, and they are going to provide the O minus, and then we're going to have the Na plus right next to it. We're going to have this 3 times that's being made, because we have 3 of these, 1, 2, 3. So when you draw your products in your ALEKS template, that's what we need to draw it down here. All right, so we have our glycerol that's shown, 1, 2, 3 carbons, OHs off of each of the carbons that's shown. And then we have our salt of the fatty acids. We have a C double bond OO, CH2 5 times, CH with a double bond to another CH, and then we have our CH2, CH3 at the end. And at the other end of the molecule, we have our C double bond O minus with the Na plus floating around right next to it. Right, so this is our salt of the fatty acid down here. That's the soap. And then we have our glycerol, which is the alcohol.